Josh, can you solve this problem regarding matrices in linear algebra? Find the parabola y is equal to a x squared plus bx plus c that passes through these points. These 3 points, 1, 1, 2, 1, 2 and -1, and 3 and 1.
So to solve a linear algebra problem, first you need linear algebra. So convert into linear algebra. So we can substitute those values there. And now we can express as an augmented matrix. So an augmented matrix is this. It's a matrix,
It's an
but
array of
we're going to put all of the numbers first.
of the coefficients, array of the coefficients.
And then now we have a line separating them, and there are those answers. So the left hand side of the equation placed on the right hand. So now we have this ABC and this R1, R2, R3. So we represent them by rows. So what the allowed operations are interchanging them. Of course, why is it allowed? Because we can change the location of these equations and nothing would change. Of course, nothing would happen because it's just the relation in space, so nothing happened. For the actual reason why Gaussian elimination works, it's a much harder This is a much harder question. So for now, the allowed operations are adding the rows, multiplying the rows by adding or subtracting the rows, multiplying or uh dividing the rows by a certain coefficient that's a constant, not another row. So we can subtract those products of a given row with a certain constant. So now this is what happens when you execute that. So R2F is R2I minus R1. So we have eliminated this term. So our goal here is to make this form. We want to make this. Wait. Huh? We want to make this zeros. We want to make all of these zeros. So whenever we want to make a matrix, let's say it's a given 5 by 5 matrix, blah blah blah. You can draw a triangle starting from here. 4, 3, 2, 1. We want this to be zeros. So that we're going to use the allowed operations in Gaussian elimination to achieve that goal. So now we have this one, it's already 0. So now we're going to eliminate this part. So the common strategy is to start here, the first term below the first first term, the first element before below the very first element of the matrix, or the top left corner. And then we go down the first column. So now we're going to make this 0, which is what we did here. And then we go on to the next column, and then we do the next 0, which is supposed to be 3. So after this, we're going to eliminate 3. So we're going to eliminate 9 first. So now 9 has become 0. We only need to eliminate this, -6. So how we're going to do that? We're going to subtract 3 times R2. So this will be -6 when we multiply by -3. So now we have achieved this form. It's called an upper triangular form. When these are all numbers that are non-zero, and these are zeros. So as I showed earlier, let's say there's a 5 by 5 matrix. It's supposed to look like this, sort of, for any matrix, and all of these are zeros. So all we need to do is express these express this matrix as an equation. So immediately as I showed earlier, C is in the third column. So 0A plus 0B plus 1C is equal to 7. So 1C is equal to 7, C is equal to 7. So similarly here, negative 2B minus 3C is equal to negative 5. Substituting the 7 we got earlier, we can get B is equal to negative 8. Ah, not showing up anyway. Not to worry. It's not showing up, but doesn't matter. We have to go. We have to keep moving forward. So, wait, let me fix this very fast. There. So now and I hope you can see the purpose of the upper triangular form. We're going to get this one as some sort of constant, so we can get the last variable. Because everything else is 0, we can finally conclude that, let's say, this one, 7, is equal to 1 of the last variable, which is C. And then after that, we can substitute it on the second column, so we can get this, which is B. And then we can substitute 2 of them here, so we can get this in the first column, which is A. Because negative 8 and then C equals 7. Okay. So now for a new and much harder problem. So let's say there's this equation with 4 variables now. So we make a matrix first, an augmented one, and put all of the values inside. I have labeled the columns and rows as x1, x2, x3, x4, x1, x2, x3, x4. This extends to any matrix at all, actually, not just all matrices. The first row, the first column on the left is the first variable. If you're using the first column as the first variable, of course. I don't know why we would not. Maybe some crazy people would put x4 here and then x3 here and then x1 here and then x2 here, but I don't know. So the first row will be, we'll call the first row, once you get down to this once you get to upper triangular form, we should be able to get x1 from this equation, and then x2 from the second equation in the second row, and then x3 from the third equation on the third row, and finally x4 should be taken from the last equation on the last row.
Yeah.
So now we can apply Gaussian elimination. So as I said earlier, we can now we're focusing on removing this one, R2. We need this term to be 0. So we don't want it to be another constant. If you can see, I switched these rows. It's because this one will be 0. It will be easier to calculate with it. So now we can finish it up. And then here we go. There's 0 already here. So our next goal, our next target is negative 2. So this is what we're going to do. We're going to use 3 variables now to collapse in. 1 plus negative 3 plus 2 is equal to 0. So we have a 3 variable combo. So now that is row 3. So now our next target is this negative 3. So R4 is equal to the new R4, R4F is equal to R4 initial plus 3R1. So this would kill off negative 3. And finally, we will have the first column free of any variable except for the first row. Our next target is this one, 3. And then our next target is 7. Now we will need to be using decimals or fractions. So it's okay if you need to use any fractions or any decimals. So now our final target is 27. So sadly, it's much easier. Instead of using any of these second and first columns, that would reset whatever progress we already had in removing the first and second elements of the fourth row. So why use them? So it will be much easier if we just use this third row, take away this term. However, we have no choice but to use a very ugly decimal, which is 27 over 10 or 2.7. Uh, it's very forced, but we have to do it. So be 0, and then we have achieved upper triangular form. So if this, let's say this matrix, it's a 4 by 4 matrix. This is a diagonal, the diagonal full of x's. Also, similarly, this would also be a diagonal. So for upper triangular form, a more rigorous
The principal
definition.
diagonals, right?
Huh?
Principal diagonal ba yun?
Not necessarily, pwede diagonal lang. Okay, so there you can also the more rigorous definition of upper triangular form means everything on to the upper right of this diagonal can be a constant or it can be 0, doesn't matter. As long as everything on the other side of the diagonal, which is the bottom left, is negative. There's
Bottom left
also
is the
something
principal
called,
diagonal.
yes, there's also something called lower triangular form, which means that we can use either this diagonal, this would be the zeros, or these would be the zeros. Doesn't really matter. For larger matrices, the same definition still applies. Let's say for odd numbered matrices, the diagonal is from the top, very top right, the top left corner to the very bottom right corner, or from the bottom left corner to the top right corner. It doesn't matter. You can pick whatever you want. So now we can finally substitute for -9, x4 is equal to -18. So therefore x4 is equal to 2. Now we know this, and this, and this, and this. We can find out this. And then once we find out x3, we know this. We can find out x2, and then we can find out x1. So now I hope you see what we're trying to do here when we achieve upper triangular or lower triangular form. So doing all of the algebra, we can get x4 is equal to 2, x3 is equal to 4, x2 is equal to 1, and x1 is equal to -1. If you want to check this out for yourself, you can substitute the values in these equations. So anyway, that's how to put a matrix into a put equations into a matrix, especially a square matrix, and make an augmented matrix. So this is how to solve linear equations in matrices, do a Gaussian elimination, and achieve upper or lower triangular form. And finally, solve the equation. There. So,
Nice. So,
thanks for watching.
thank you.